Defining science. There is no single definition of science that everybody agrees upon. And so there's quite a bit of debate on the issue. One definition is the search for naturalistic explanations of all events. But this is an imperfect definition. This definition, I think, was given by the Kentucky Department of Education when they were writing their science standards. This first definition is imperfect because it has an assumption. It's an assumption that everything has a certain kind of cause, a naturalistic cause, and that cannot be proven. But science has assumptions all the time, and they are taken by faith. You have to have some kind of assumptions to do just about anything in this world. You can't avoid it. Most assumptions are, of course, agreeable to everybody. Some assumptions are controversial. Something that's agreed by everybody is that if I do an experiment today on dropping baseballs from a balcony, I'm going to get the same results as if I take it tomorrow and the next day. You know, assuming the weather is the same and all that kind of stuff. But, you know, if I drop a baseball inside my house from 3 feet, it's going to hit the same speed today as it will tomorrow and the next day. We can't prove what's going to happen the next day, but we assume that's going to be the same. Okay, continuing. Most of the debates in science today are about whether or not an assumption is valid. When you have a debate with others, you may want to openly check with each other. Are you assuming this, or are you assuming that? And maybe that's the center of your controversy. A second definition is better. The study of matter and energy. It's shorter, it's more to the point, I think, more basic. What are the traditional ways of describing the steps of the scientific method? You don't have to write these things down, but first of all, you want to, oftentimes it's said that you want to state the problem. Exactly what are you going to be studying? The more specific, the better. And then you want to research. Maybe somebody has already found out what the answer is. Or maybe they did some research and they at least found out what the answer is not. Or maybe they just nibbled around the edges a little bit and got some hints. Okay, research. And then you make your hypothesis, your educated guess as to what's going on. And then you perform a test of some sort. And from that test you make observations and measurements. And after you make the measurements, then you're going to organize your data. And sometimes that will be included with analyze the data. And as you analyze the data, you come to a conclusion. Now, by organized data, I mean you're putting it into tables and graphs. Analyzing the data, you're applying some equations of some sort. Conclusion, you're looking at the equations and seeing what the relationships are, if there are any. Maybe there aren't. And sometimes you can even go on and you can say, well, then I'm going to make a prediction with my conclusion. And then I'm going to further test that prediction. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps to this listing. But it's important for you to understand that there's no official steps for the scientific method. I have 10 steps here, but I've seen as many as 13 steps in a textbook, and I've seen it condensed down into 5 steps even. So there is no single official thing that has been described. The main idea of this method is that research is done in a logical and repeatable way. And yes, you can do science without these steps. For instance, a lot of ecology is just simply keeping track of the populations of things. So there are people who get paid for just simply flying over Canada and counting polar bears, and they are considered ecologists. So they fly their airplane back and forth in a grid-like pattern to cover giant areas, and they just simply look out the window and count polar bears, and they indicate where they are found. Limits of science. Science cannot study everything or answer every question. It cannot answer questions about whether something is good or bad or if it's right or wrong. For example, is that a good painting or a bad painting? It depends on what your values are. For some people, they only like very realistic paintings. Abstract stuff is just too confusing to them. And other people get bored by realistic stuff. They say, oh, that's what I see every day, every time I look. I like this abstract stuff that gives me more imagination and creativity. You cannot judge if something is right or wrong. Is a treaty the right thing to sign, or is it the wrong thing to agree to? Those things are not scientific statements. Now, science can say what will happen if we do sign the treaty or if we don't, but whether or not that's a good idea or a bad idea, a right or a wrong decision, is based on the values of the politics of the situation. You have to take everything into account, and some people value one thing much more than another, contrary to other people. Okay, next. If you cannot use an instrument to measure it in some way, then it really isn't science. So there is no instrument that we can point at a piece of art and the needle on that instrument goes up to whether it is good or bad on a scale of 1 to 10. You cannot scan in a treaty and have the machine decide if that's the right thing to do or the wrong thing to do. Because scientists have been so successful in improving our lives, it's easy for us to give them permission to cross the limits of science can do and can't do, and we give them the authority to say how we should live our lives. An example of this is the pandemic stuff. We can listen to different doctors and they can say, if we do this kind of behavior, then we expect this kind of infection rate. That is perfectly fine way of a scientist talking and trying to explain things as best as they understand. But when they start saying, therefore we need to pass certain laws to close down these businesses and to restrict this kind of travel, now they're not talking about science anymore. Now they're talking as a regular person, and that is perfectly fine. They have that absolute right to give us their opinions. But the idea here is that when they start saying what kind of businesses should be allowed, what kind of travel should be allowed, now they are playing a value system. Do they value the health of a certain number of people over the freedoms of certain people? The health of some people versus the livelihood, the income, the mental well-being of other people. There's the discussion of we want to close down outpatient surgeries, testing of hospitals, because we don't want the mingling to increase the infection rate. If we allow people to come in for their cancer monitoring, that's going to allow more people to get together, which is going to make more COVID cases. And they don't want that. But now they are weighing the value. Do we value the patients of COVID or do we value the patients of cancer? We are saying that the cancer patients are not as important because they aren't getting the monitoring like the COVID folks are. And so when they start talking about policies, they can give us their opinions, and that's perfectly fine, but they're no longer talking in the realm of science says this. This is, let's see here, how we should live our lives. That is not part of studying matter and energy that they are experts in. And so there isn't a tool to measure laws or ethics. Science cannot study the supernatural. This prefix super means above. So supernatural means above nature. This does not discount or disprove the existence of things that are above nature. It just says that the direct study of such things is not the realm of science. There are no instruments that can measure things that are not matter or they are not energy. So the supernatural that's not matter, the supernatural that's not energy, cannot be studied by any instrument that we have, and so therefore it's not science. You have to be able to use instruments somehow to measure it in some way for it to be science. Remember that the scientific method is an aim to do things in a logical and repeatable way. There is much, though, that is done in the name of science that is not repeatable. One such type of science is called historical science. It tries to come up with possible explanations of past events, but such explanations cannot be proved. We can get good guesses on them, very reasonable things, but they cannot be proved. The measurements and observations that the researchers use in their reasoning can be repeated, but the event that is actually being discussed cannot be repeated. The conclusions cannot be repeated. Okay, another limit of science is that science is not omniscient. It means that it cannot know everything. And this will be discussed later on in the reading. But one of the examples I'll just briefly mention is that you cannot know the speed and location of something at the exact same time. We can know the location of it, but that's just one spot. To find the speed of something, you have to know its location in two spots and the time in between. So when you're moving it between them, then you don't have a specific spot anymore to know its location. So you cannot know both speed and location at the exact same time. Another limit of science is that science is not infallible. Infallible means mistake-proof. And there are lots of examples when scientists have made mistakes. And hopefully they have corrected themselves. Another prime example here during the pandemic of 2020 is at first they said, oh no, don't wear masks. The public does not need to wear masks. And then later on they changed their mind and they said, oh, okay, now we have new evidence and now we change our minds and now we're saying that you should wear masks. If science can be wrong, scientific statements must, since science can be wrong, scientific statements must be stated in a way that are falsifiable. You have to be able to, at least theoretically, be able to prove a statement false for it to be considered science. If there is no way that you can prove it to be right or wrong, then therefore it's not falsifiable, it's not really science. For instance, there are some folks who have said global warming is going to cause more snow. But at the same time, there are other folks who say global warming is going to cause less snow. So with just that bit of information, it's not possible to prove global warming right or wrong, because as we look at the records into the future, if we find out there's less snow, there's going to be some people who say, see, look, you've proved my point. But if records show that there's more snow, there'll be other people who say, yep, look, I've just proven global warming to be true. So just on that little bit of evidence, it's not falsifiable. We have to take into account a lot of other stuff, and yes, people are doing that, and that's a whole nother discussion that we will get to the second semester. To catch errors, science uses the process of peer review. This is when peers of the researchers, in other words, other similar researchers, read over the lab reports and make sure that no mistakes were made. Preferably, the peers will actually redo the experiment, but unfortunately, few researchers have the time or money to actually redo the labs. For the most part, we just have to have faith that they did things as written and the results were recorded in the lab. Sadly, this is not the case in many times. There are cases of scientists just simply blatantly cheating. When they were looking at mice, for instance, I don't know exactly what the experiment was, but it didn't turn out the way they wanted to, and the scientists actually ended up, I don't know if it was painting or taking a magic marker to the mice to change their colored spots or something like that, putting black marker on them. I'm not sure exactly what it was, but it was kind of a big fuss when it happened way back last century. Here's an excerpt of an article about the weaknesses of modern science. Peer review process guarantees little in the terms of trustworthiness, even before political agendas compromise the issue. When studies are replicated, they rarely come up with the same results. Only a third of the 100 studies published in the top 3 psychology journals could be successfully replicated in a large 2015 test. Medicine, epidemiology. Epidemiology is a study of epidemics, I believe. Population science, nutrition studies fare no better. When only a third of the peer-reviewed studies reach the same results as when they were replicated by outside authors, there is a serious problem. 33% of the time they're right. 66% of the time, maybe not. Now, this is not to say that science is worthless. I still believe that science is the best way of figuring things out. But the moral of the story is that science is not mistake-proof, and just because something is published in a journal or in the newspaper does not mean that it is true. In fact, every single time that you read about some kind of a scientific study, most likely it is not true. However, it is still the best way for us to figure things out. And as we work through life, and as we do more and more replications, then we get closer and closer to the truth. So a single study published in a journal, it's a nice hint as to what might be true. But we need to have lots of different people attacking the same question in lots of different ways. And then, after we see lots of the similar results, then we can say, all right, now we can talk about what is probably true. With the pandemic, there's all sorts of talk about different kinds of medicines and whether or not they are good or not. Some studies say that the medicine is good. Some studies say the medicine is bad. Everybody has an opportunity to uphold something and say, look, here's evidence for my side. However, if you look carefully at the studies, they are all different in one way or the other. And so they're not answering exactly the same question, because just simply the matter of fact that they are working with different human beings, with different DNAs, you're going to have slightly different results each time. But there's also the idea of how sick are the people, what kind of environment are they, how old are they. All sorts of different things come into play that could affect the results. So you can't just look at 1 or 2 studies and come up to a conclusion. You have to look at lots and lots and lots of them. Okay, therefore, science is never settled. No idea in science is above criticism. Any idea can be proven wrong if the data goes against it. The number of scientists that believe something, that is not proof that's true. Even if 99% of the people believe that something is true, it does not make it true. It makes it the best guess that we have. And we should act on that, yes, that's fine, but don't discount things that go against it just because of this consensus. If proven data contradicts a scientific law, in other words, we do it again and again and again, and it keeps on contradicting the scientific law, then the law needs to be changed or tossed out. Even the law of gravity. Or let's go to another example, the idea of how many dimensions are there in the universe. Okay, there's up, down, left, right, forward, and back. There's 3 dimensions. But in the last few years, I'm not going to say exactly how many, but in modern physics here, there's actually the idea that there might be 11 different dimensions. That's kind of a weird thought. The law of gravity is that everything falls down at the same rate if you discount air friction. So if you have a vacuum chamber with no air friction, a feather will fall just as fast as a baseball. That is accepted science, and just about nobody disagrees with that right now. But back in the 80s, there was somebody who was doing an experiment way down deep in a mine shaft, And they came up with some really convincing data that showed that copper might be falling slower than steel, which might fall slower than another kind of metal, which, different kinds of metal falling at different speeds. And their data was really, really good. It was so good that Boeing Aircraft Company and the U.S. Air Force gave this guy several $1 million to continue his work, because they were thinking, hey, if we can make airplanes out of the right stuff, maybe they'll just fly on their own without having to have engines burning fuel. That'd be fantastic. So even that settled science of the law of gravity was willing to be tossed out because of this guy's data. Well, it turned out that after more study, it turned out to be nothing. And so he had to go and find something else to study. But anyway, it's evidence that even basic ideas can be disagreed upon. Okay, next. How science should debate. Scientific debates occur when a lab is published and people argue over whether or not their analysis of the data is correct. Such debates need to be based on the data and the procedures, or maybe even the equipment being used. Without these, the conversation would be considered philosophy or something else. So, without being based on the data, without the conversation being based on procedures or materials, then it is not science. Debates, unfortunately, often stray from data and procedures and become unproductive. An ad hominem attack. Ad hominem means to the person. This is Latin, to the person or against the person. An ad hominem attack is when you criticize the person instead of the person's data or procedure. You might say, oh, that person really isn't a good scientist. He just got his degree from this rinky-dink college down here. He's not all that smart, so we can discount his data. We don't even have to look at it. Or there's something wrong with his data because, man, he was wrong about that other report, and so therefore I'm not even going to believe him this time. So we're not looking at the data that was presented, but rather the person and that person's history. That is an ad hominem attack. This is an inappropriate, improper way of debating, but unfortunately it's a rather common one. Name-calling and ridicule are unfortunate aspects of many debates. That's because these debates are being taken by people, and people are always fallible. They have their frailties and problems. This is a kind of logical mistake in debates. There are many other logical mistakes that people make when they debate an issue, including science. So debating any issue like philosophy, science, politics, psychology, all sorts of things. Many of these mistakes are called fallacies, and throughout the year we'll be looking at many different kinds of fallacies. So here's a newspaper article about a scientist, Mr. Sheckman, and he discovered something that went against settled science, and people did not like him. He called them all sorts of names and tossed them out of research groups and such. So I want you to read this, and I want you to see how ad hominem attacks were used. Go ahead and look at that now. Pause the video as you read this. Okay, here are the two that I saw. Quasi-scientists. So they made up a new curse word against him, and also they attacked his history. So they weren't attacking his data. It turns out that his data was right, and later on, I find it kind of funny, they actually found out that some of the scientists that were doing the criticizing, they went back to their old experiments, and they found the same results without realizing it. Okay, refocusing on today's purpose. Today's purpose was, I will define the term science. I'll be able to define what science can do and what science cannot do. Have we covered all of those things? We've defined science as the study of matter and energy. We've explained that it can study anything that is measurable, and we said that it cannot know all things, be omniscient. It cannot be mistake-proof or infallible. It cannot discuss right or wrong. It cannot discuss good or bad. It cannot discuss things that are not falsifiable. So yes, we've covered all of today's purpose. Here is an article if you want. It's optional. when 99%, 98.9% of people in the science realm were wrong about something. And then here's an article about falsification. Oh, there we go. I'll let you read that article on your own. I do believe there's going to be some homework problems on this article, but on the previous pages, this really, really long article about the eggs, this one here, there are no homework questions on that. That's purely optional for you. Now, on this page here, this is good. Some of the lessons have this, not every one of them, but a lot of them do. And it's just a written version of the lecture that I just gave. So some people prefer to just simply read this instead of watching the videos. So in the future, if you see this kind of a feature, you could skip the video and look at this instead. Okay, at this time, would you please go to Schoology and do the wrap-up problem and the homework problem for the lesson.